All right, let's talk about solving exponential and log equations. Now, this is the first of two videos. This video is basically going to address exponential functions, similar to that 3 to the x equals 81 up here on the upper left. The second video will address equations more like the one on the right, the logarithm base 4 of x equal to -2. We're going to address what do you do when you have a logarithm that starts in the equation. Again, this video is basically going to address when you were starting with exponentials, such as, again, those examples down at the bottom. And I'm going to move fairly quickly. Feel free to pause the video at any point to record all of the steps or to kind of go back over any of these equations. Again, the nice part is most of the time we're just solving equations. We're just going to approach this the same way we always have algebraically to solve. Whatever the last thing happening is going to be the first thing to go. So when we're looking at an equation such as the one at the left here, again, in that -15, if I was thinking about order of operations, right, checking my answer, plugging something in for x, I would do 9 to the x minus 15. So let's add 15 right away, right? And again, I'm not going to show necessarily all the time those steps, but again, the basic idea of this is we're just adding 15, right, to both sides. So again, I'm going to add my 15 on both sides. That's our basic algebra steps. -6 plus 15 was 9. And again, now, and here's the big step, how do we get rid of that 9 to the x, right? How do we get rid of that base 9 so that we have just x? Now, you can do this in multiple different ways, but really, with this problem, as the directions say, for some exponential equations, it's just easiest to use your head. If 9 to the x equals 9, well, that's really 9 to the first. Well, if 9 to the x equals 9 to the first, you have equal bases. They're equal to each other. The only possible way that could happen is if x equals 1, if the two exponents are equal. And again, that would just make sense in that problem. And you could double check it at the beginning. 9 to the first would be 9. Minus 15 is -6. And again, that works. That's what we wanted to have. So let's use that same idea on the next one. We've got 36 to the 5x equals 6. Well, 36 is really 6 squared. And power to a power, we know we multiply our exponents. So 6 to the 10x equals 6 to the first, which means 10x equals 1. Right? Equal bases equal each other. Let's get rid of those 6's. And then finally divide by 10. And we should be in good shape there. X equals 1/10. And the same thing goes on the right. Again, to get rid of that 3, we're going to divide by 3 or basically multiply by a 1/3, right? Multiply by 1/3 on both sides, which makes that 1/36. Again, 36 would be 6 squared, so 1 over 36 is really 6 to the -2. And again, if they're both base 6, then x must equal -2. And again, you can plug that -2 back in, check your answer, and make sure it works. On the second screen, same thing. Now we've got e to the power, right? So now equal basis isn't going to be quite so simple. But that's why we have logarithms, right? Again, to get rid of an e, a base e, remember that exponentials and logarithms are inverses of one another. So the first thing that I would do is take the natural log on both sides. The natural log of the left, the natural log of the right. Natural log of e, remember, cancels away. So again, that's just going to disappear. And we're going to get x plus 8. Now it's no longer up in the exponent, though. A great way to get rid of the base. Natural log of 14 is a number I can type into the calculator whenever I'm ready. But at first, I want to subtract that 8 from both sides, right? Just like we did on that first screen. Let's do some basic algebra. Subtract 8 on both sides. Now, you do want to be a little bit careful when you go to type this in the calculator. Remember, the calculator, when you type in natural log, typically is going to put a parenthesis here. If I don't close that parenthesis, it's going to think 14 minus 8 is all inside the logarithm. But remember, up here, that 14 was the only thing inside the log. The minus 8 came afterwards. So don't forget, make sure you close that parenthesis so that we type in the natural log of 14, close that parenthesis, minus 8, and you should end up with -5.361 approximately. Again, the natural log of 14 is an irrational number. It's going to be a nice long decimal value. We'll round accurately to 3 decimal places there. We can use that same idea on the next page. Again, the first thing I would get rid of in this upper left problem would be dividing by 4 on both sides. Gives you a 5. But now since we're base 10 over here, I would say let's go ahead and use a common logarithm. Log base 10 of 10, right, is going to be a good idea. So let's use a common logarithm on the other side as well. And again, that's basically going to leave you with common log of 5 on the right. Log base 10 of 10 cancels and 3x is there. We'll divide by 3 very simply. Again, making sure that division by 3 comes after we've done the logarithm. Log of 5 divided by 3, which again will be approximately 0.233. Now, the next problem has a couple of different options. The first step is really, not optional. We want to add 8 to both sides, right? So we're going to get 20 on the right side. But now it's our choice. Kind of like the last two problems, if we're at 7 to the x, we're probably due to use a log base 7. So if we want to use the given base, if 7 to the x is what we're trying to kind of mess around with here, then log base 7 of 7 is a great idea, right? Because that's going to go ahead and log base 7 of 7 cancel away. And we'll simply get x equals log base 7 of 20, using a little change of base formula in case you don't have a calculator that can do a log base 7. Change of base, log of 20 over log of 7, we'll get 1.540. Now, you don't have to use a log base 7 if you don't want to deal with that change of base formula later on, or you don't like using logs that aren't common or natural. You can absolutely use a common or a natural log. I went ahead and used a common log because now we just need to remember the property that if log of 7 to the x is here, well, why not pull that exponent down in front, right? We got an exponent property that does that. X times log of 7 equals log of 20. Divide by log of 7, it's really just a number anyway, right? And notice that's the same thing we had on the other side, right? It's really the same statement, right, that we had right over here. So again, we're going to get that same value that we got last time, 1.540. So it works either way. And you could also, again, could have used a natural log, that same move of pulling that exponent out, right? Pulling that exponent down in front. That's really the big step if you use a common or natural log when, that wasn't really going to cancel the base. All right, quick brain buster here for you. This one's tricky. So again, I would pause the video if you want to take a shot at it. Otherwise, I'm going to keep on going forward here. First thing that I'm going to do is take a good look and say, all right, this looks like a mess. But this is really something squared, something to the first power, and a constant. It reminds me a lot of a quadratic. So if I pulled out that e to the x, right, maybe we'll call it u. Do a little u substitution when you get to calculus. That'll make a lot of sense. You do that a lot. U equals e to the x. So therefore, e to the 2x is really just u squared. E to the x would be the u. Now if I can factor equal to 0, then I could just take that u back out again, put those e to the x's back in, right? Or if you can just factor straight away, you go right ahead. But if you FOIL these two back together, you distribute those two things back together, I guarantee you'll get right back to that original statement. In that case, then we just split it into two parts, right? Solve them separately equal to 0. Quick little subtraction, quick little division, and a couple of natural logs. Now, natural log of -1/2 doesn't really work. That's undefined, right? Or actually, technically, we would call that one an extraneous solution, right? EXT, that one's extraneous. You can't take the natural log of -1/2. Oh, sorry about that. Can't take the natural log of -1/2. So it's not really going to work too well as far as that goes. But you can take the natural log of 5. So 1.609 there. One last problem, just to show you where we can use this in real life. Again, we've talked about continuously compound interest before. So if you want to double your money, basically it doesn't matter what principal you start with. We want to end up with twice that much. And if I divide the p away from both sides, then I can quickly take a natural log on both sides, right? Cancel that e. Divide by my rate, very simply. And if I type it in, there's how long it will take. I don't know why that's labeled as money. How long it will take, 23.10, and I believe it was a 5, if I remember my numbers correctly. 23.105. And again, it's an APR, so that's going to be years, right? It's an annual percentage rate. So we were measuring in years. All right, hopefully that helps you solving exponential equations. If you have any questions, talk to your teacher. Otherwise, have a great day.